Well, hello and welcome everyone. So this is the second in a series of 3 seminars related to earthquake design for uncertainty. So this is an initiative that's been born out of the recent release of the new National Seismic Hazard Model. Obviously that's created some questions around the broader profession in terms of what that might mean, or probably more importantly, what it doesn't mean for immediate practice, but also touch a little bit on the longer term and what the process might be over the next few years to see in any way that might contribute to potential future code changes. So in terms of the response to the National Seismic Hazard Model, the initial thing was releasing the Earthquake Design for Uncertainty document earlier this year, and also the interim guidance document that came out recently. So that was a joint effort between NZSEE, SESOC and NZGS. So the same 3 technical societies have joined together to produce the seminar series with some support from MB. And we had one yesterday, one in Wellington, one today here in Christchurch, and then the final one in Auckland on Friday. And then today's one is also being live streamed to people around the country that couldn't make it to one of those sessions in person. So we are also recording the seminar, and we'll make that available through the technical societies in the wake of, in the next week or so. So for those of you that don't know me, I'm Jeff Rogers. I'm a professor here at Mechanical Engineering at the University of Canterbury, and I'm also the president of NZSEE. So that's it's organisational involvement in this seminar, but it's very much across to the presenters for the work that they've done. So what we're going to do today is we'll run through. We've got 4 presenters, which are outlined in the brochure that you were sent. I'll give a short introduction to them shortly. We'll have them present. We'll have brief questions after each presentation, and then a larger group of questions. So that's the outline for today. I just want to introduce the speakers very quickly. So first of all, we have Professor Ken Elwood, who's the MB EQC Chief Engineer for building resilience. And so Ken's a professor at the University of Auckland. He spent extensive time at the University of British Columbia, about 11 years on faculty there before moving to the University of Auckland. He was the inaugural director of Te Hirangaru Quake Corps, and is now in the secondment role as the MB EQC Chief Engineer. We also have Andrew Thompson, who's a technical director with Homes and the Building and Structures team, and he's based in Tamaki Makaurau, Auckland. His role encompasses project delivery and technical leadership. He's been on the NZSEE Management Committee since 2019. And is also the NZSEE representative on the Joint Committee for the Seismic Assessment of Existing Buildings. So Andy's also been a contributor to the Design for Uncertainty guidance and the Interim National Seismic Hazard Model guidance that was issued earlier this month. So he's contributed significantly in different ways. He's also on the Steel Structures P3404 Committee. Mark Willard is an engineering advisor at the Ministry of Education, where he provides technical leadership and oversight of the Ministry's seismic resilience policies. He's also a chartered structural engineer, and Mark chairs the Ministry of Education Engineering Strategy Group. So the Ministry is being very proactive in this area, and there's some really great lessons to be learned from the broader Ministry experience, and that's provided by Mark. And then finally we have Sjord, who's Senior Geotechnical Engineer and Technical Director at Tonkin & Taylor. So Sjord has experience as the Director of Geotechnical Group, comprising over 200 geotechnical and engineering geologists, and is responsible for technical development and technical mentoring of engineering staff, technical liaison with industry and research institutions. So we've got 4 really exciting presenters.
Let me ask you a question. Who here has heard of the National Seismic Hazard Model? Anybody who didn't put up your hands, what rock have you been under and how stable is your rock? No, of course you've heard of the National Seismic Hazard Model. It's been the biggest thing going in our business for the past several years. You've probably heard and had some understanding that this was likely going to lead to increased estimates of ground shaking in New Zealand for some time. Then that was confirmed with the release of the National Seismic Hazard Model earlier this month. And So now we ask ourselves as engineer, what's next? And so really that's what this the seminar is about. It's about considering the results of the National Seismic Hazard Model, what we as engineers can do in this time in the light of the National Seismic Hazard Model, and a little bit about where things might be going in the future. I'm really pleased to be here, to be representing MB in my role with MB now. And I'd like to share with you a little bit about what MB's doing in this regard. But first, I want to thank the technical societies for putting on this seminar and trying to help the engineering community in this time of uncertainty. And really great organization putting this on. I also want to congratulate GNS and the whole team, including a considerable team here at the University of Canterbury that led the National Seismic Hazard Model. It really was an international effort. There were people from some dozen countries contributing to the effort. And really what we have now is an internationally recognized world-leading National Seismic Hazard Model. Okay, and we really should be proud of this. I also have to apologize to those who were involved in the development of the National Seismic Hazard Model, as I would like to start off with a, oh, this is not working. All right, so where was I? Yes, I was saying that I'm apologizing to GNS for my oversimplification that I'm going to give you here of the National Seismic Hazard Model, what it was. Really, the National Seismic Hazard Model has two main components to it. One component is identifying the faults throughout the country. Okay, so when my little sketch here, here's a fault. Of course, there are thousands of these faults throughout the country, and some of these faults will actually link up with other faults. This is all considered in the development of the National Seismic Hazard Model, and each of these faults has a range of different earthquakes that it could produce, different magnitudes, different rupture scenarios that are considered. That's one side of it. Then the other side is when that earthquake fault ruptures, the waves from that from the movement on that fault travel through a path to the site, and so that traveling wave is approximately represented. How it travels through the site and maybe perhaps gets amplified by the site conditions is considered. But the end result is the shaking at the site. And it's to capture what happens in the ground, the peak ground acceleration, and what happens to a single degree of freedom, the spectral acceleration. Okay, and one thing I want to emphasize is that these are peak values, right? Of course, the PGA is simply that peak value from a much more complex ground motion. The National Seismic Hazard Model is just these peak values. It's not the actual ground motion itself, okay? And here I have to resort to a little bit of teaching in my new role. I don't get to teach as much as I used to, so please bear with me. But I think it's a good idea that we all start with the same basis. So let me explain to you exactly what the response spectrum is. Please bear with me. And the response spectrum is essentially capturing a summary of those peak values of response of the structure, okay? As opposed to the PGA, the peak of the ground motion. So I've got a ground motion up there on the top. I run that ground motion through a whole bunch of lollipops, single degree of freedoms with different periods, 0.5 seconds, 1 second, 2 seconds is shown there. And I get some peak displacements. And I summarize those peak displacements in a displacement spectrum. That is the output of the National Seismic Hazard Model. That is then converted to an acceleration spectrum, but we actually call that technically a pseudo-acceleration spectrum because we arrive at that by simply recognizing the relationship between displacement and acceleration of a single degree of freedom, which is to multiply the displacement by 4 pi squared over t squared. Don't worry about the details, but that's how it's done. But I put pseudo there in brackets because we often just drop the pseudo, because if you compare that to the actual total acceleration that's measured, the peak value, it's almost exactly the same, all the way up to a really large damping value. I mean, we're talking like around 15–20% where they start to diverge. So for all intents and purposes, the pseudo acceleration spectrum is equal to the acceleration spectrum, so we tend to just drop the word pseudo. Okay, and why do we want that value? Well, we want to know the base shear to be able to design our structures, and so we know mass times acceleration equals force, right? So the base shear is just that, but we tend to work in terms of weight times spectral acceleration, where that spectral acceleration is simply expressed in g. Okay, and that is the basic equation that is in 1170 that we all use for the design of structures. All right, so teaching's done. A bit more on the National Seismic Hazard Model, what it is and what it isn't. The National Seismic Hazard Model is exactly that. It is the hazard, the ground shaking hazard. It is not risk. Okay, risk is really capturing the impact on society. And that really is about capturing the performance of the buildings. And that really is our next step, right? And that's what we need to figure out now, is how do we interpret the hazard in terms of the risk on our buildings and infrastructure. But the National Seismic Hazard Model does provide really important input for risk-based decisions. And really what we're talking about there is we need to assess what our risk tolerance is. And based on that risk tolerance will help us determine what values out of the National Seismic Hazard we actually want to use for design. In other words, what return period does one use for design? We often think of 1 in 500 years, right? But that's not been written on stone tablets somewhere. It's convention. So let's take a moment and think about what is the risk and use that to guide our design decisions. Some of the key changes within the National Seismic Hazard Model, which are impacting the outcomes, the forecasts, are on both the earthquake rupture side and the ground motion side. And a big part of it is data. You know, there's so much more data than there was 10 years ago when, or 12 years ago when the 2010 National Seismic Hazard Model came out, and way more data and models available than there were back when the 2002 model came out, which is really the basis for our 1170.5. There's also been a lot more consideration of lower seismic regions and what sort of seismicity we might expect in those areas. Notice I said lower, not low. I think we got to stop referring to any part of New Zealand as low seismic regions. And another big consideration is the Hekurangi subduction zone. This subduction zone, while there's still a lot for us to learn about it, we know a lot more now than we did back in the 2010 model. And so that's one of the big features that's really driving some of the changes. And there's not just one ground motion model now, there's several ground motion models that are considered, and the outcomes of all those ground motion models are considered in arriving at the results of the National Seismic Hazard Model. But one of the biggest impacts of all is how side effects are captured. And they are captured in the new National Seismic Hazard Model through a term called VS30. What is VS30? VS30 is the average shear wave velocity over the top 30 meters of your site. And Sjord is going to go into a lot more detail on the VS30, but let me just highlight a few things here. So first of all, the VS30 has been used in international standards and actually is used within 1170.5 currently to a certain extent. But in 1170.5, the sites C and D are not distinguished by VS30. And really, a lot of our sites in New Zealand cities are in that C and D range. And so that's a pretty important range. This is the main way in which sites are classified by international standards, and some examples are shown there. It is the only parameter used within the National Seismic Hazard Model to reflect site effects, that amplification or of ground motion waves that I showed in the first slide. And all of the ground motion models that are embedded within the National Seismic Hazard Model use this term VS30. So really, it's the only term that can directly relate to the outputs of the National Seismic Hazard Model. So we're kind of stuck with it. It does provide us with a single measurable parameter that reflects some important characteristics of the site, the initial soil stiffness, and in some cases, the site period as well. It may not be perfect, but it is a consistent basis for us to use. We'll talk more about it as we go through this afternoon. But it is going to lead to a distinction of sites compared to what we currently consider. So this is some great work by Chris McGann here and his team here at the University of Canterbury, where they've identified the VS30 for sites in the Christchurch region and compared that to what site classes they would be classified as. And you can see the wide range of VS30 values for both site class C and site class D, and even site class E. And so depending on the type of site class C site that you currently have is going to dictate the impact of the National Seismic Hazard Model on your site. So really the impacts of the National Seismic Hazard Model are really going to be quite site specific. And we'll emphasize this as I go along. Another thing I want to emphasize is that national maps are not reliable for site-specific design. These are two national maps that are out there in the literature, but they've been color-coded the same, so you can see the huge variation in the results for these two studies. And so if you took a picture before I put up the warning, please take another picture. Not suitable for site-specific design. And so don't go looking for maps to pull up VS30. Really what needs to be done is a measurement of the VS30 at the site. There's good guidance provided for you in Module 2. And Sjord will be talking about this in more detail later on. So enough about what the National Seismic Hazard Model is. Let's look at some sample results. I do encourage you to go to this website that GNS has set up. It's a really great web tool to explore the results of the National Seismic Hazard Model. You can really geek out on it for a long time. But let me just grab a few sort of high-level observations. First of all, sort of the key message from GNS in presenting the results is that the outcome for New Zealand can range from no change to more than doubling, depending on your location and site conditions and so on. The average increase over the previous National Seismic Hazard Model is about 50%, okay? But it really depends on where you are. But they emphasize that that increase in hazard doesn't necessarily translate directly into impact on buildings and performance of buildings, and that's really why we're here talking today. What's shown in this slide is PGA, and again, it's the comparison of the 2010 National Seismic Hazard Model with the new National Seismic Hazard Model. And you can see, pretty big increases across much of the country. But we know that that from a building performance perspective, PGA is not necessarily the be-all and end-all. So, and from our perspective as engineers, we want to compare to what the design standard has in it, right? So let me share with you some comparisons that we've done to 1170.5. This is looking at Wellington. It's looking at 1 in 500 annual exceedance probability, okay? And looking at two different VS30s that are commonly found in the Wellington CBD. So 200 meters per second, 400 meters per second. And what we're showing is the ratio of the mean National Seismic Hazard Model results to the 1170 values. And you can tell that the result really depends on really what site class you're in currently in 1170. If you're sitting in a stiff site class C, for instance, the amplifications can be pretty significant. Whereas if you're sitting in a softer site, a D or maybe an E, those amplifications are considerably lower. So the results here are very much dependent on the type of site you're in relative to the VS30 that you find yourself in. Probably an even better way to picture this change is, again, I'm looking at the ratio of the National Seismic Hazard Model to 1170.5 on the x-axis of each of these plots. This is just simply, the bars are simply indicating the amount of area in Wellington CBD with that amplification. And the different charts are for different periods. Short periods up here, moderate periods, and long periods, 3 seconds down here. Okay, and this was some good work done by Anna Kaiser at GNS, where they have a pretty good model for the distribution of VS30s around the Wellington CBD that is calibrated back to available data in the region. And so they've separated that out by what locations would likely be classified currently as a D or currently as a C. And what you see is that the largest increases, again, are for site class Cs, right? And particularly in the sort of mid-period, short period, mid-period range, site class Cs giving a pretty significant increase. Whereas your site class Ds, and particularly for the long periods, are not seeing that much amplification. In some cases, perhaps even a de-amplification. That might be related more to our site class D spectrum as it is right now in 1170 than it is the results of the National Seismic Hazard Model, which I'll show you in a few slides. Another aspect I want to emphasize is that we're seeing some interesting results in terms of the shape of the spectrum and the impact of the intensity of shaking on the shape of the spectrum. Okay, so shown here are 3 return periods for Christchurch: 25, 500, and 2500. Okay, and you start to see that, well, first of all, you see this amplification from stiff rock sites up to very soft sites, as one would typically expect, right? The soft site, we all know that soft sites tend to amplify motions, right? But when we get up to the higher intensity motions, you start to see them cross over a little bit in the short period range. Well, let's look at Wellington, where, of course, the intensities are even stronger. So Wellington at 500 years, you start to get that considerably more of that crossover effect happening. And in 2,500 years, you've got far more of it. Really, the soft soils can't transmit that really intense motion. And so the soft soils end up down here for the short periods, and it's really the rock that's up at the high levels, okay? And this is something that we've known for a long time, but we haven't really reflected it in our the shape of our spectra that we use in 1170.5, okay? And I'll come back to that in just a moment. Then it's worth looking at international comparators, okay? So what we've done here is we've just chosen some cities around the world that are thought to be high seismic zones. I haven't tried to pick cities with exactly the same, seismicity level or seismic hazard or what have you. Just large cities, mostly large cities that tend to have high seismicity. And you see a range of design values. And Wellington sort of falls in the middle, but at the longer periods or the mid periods here, tends to actually be maybe a bit low for the 1170.5 spectrum. By the way, this is the site class D, so it's sort of the bigger of the main spectra used in the Wellington CBD. And if I put the National Seismic Hazard Model on there, you see, yeah, it's gone up relative to that, that spectrum. It's still, though, sort of within the range of international comparators. Perhaps the short period range is pretty high compared to a lot of sites like, say, Oakland or Seattle. But that's still to be determined whether we still really need to design right up at this peak. Okay, more on that in a moment. So we're in the right range still, even with this increase. We're not an anomaly. A point I want to make is that the hazard and design spectrum are not necessarily the same thing. Okay, and I'm going to try to make this by comparing the 2010 National Seismic Hazard Model. So this is the old National Seismic Hazard Model with 1170.5. Now, granted, 1170.5 was actually developed based on the 2002 model. We don't have all the data to give you a comparison with 2002, but the 2010 and 2002 models were very, very close. Okay, so you can take it as essentially representative of the National Seismic Hazard Model that was used to arrive at our design spectrum today. So if we look at site class C, the dashed spectrum is the National Seismic Hazard Model, and the solid line is the 1170.5. And you can see that the decision was to sort of cut off the peak of the spectrum, just typically done around the world, and also to raise it in the long periods. Okay. Now, if we look at site class D, it looks considerably different. So site class D from 1170.5, the solid line, site class D from the National Seismic Hazard Model, the dashed line. And here there's a judgment made in the development of the spectra to maintain the same spectral shape throughout the country. And this meant enveloping the results across the country. And so you didn't get that de-amplification in a city like Wellington with a high seismic hazard. So that's not represented by the design spectrum. The main point I want to make here is that designed spectrum does not equal hazard spectrum, or the other way around. Okay, and we're currently in the process of figuring out exactly what we should do, what's most appropriate for that design spectrum. So what happens next? Well, here, the first thing is nothing changes. Okay, The National Seismic Hazard Model is just that. It's a hazard model. It does not automatically change the way we design and assess buildings. Okay? MB, I'm here representing today, is carefully considering the results from the hazard model and how that's going to be applied to the building regulatory system. And this means both in terms of new buildings and the assessment of existing buildings. For new buildings, we're working with Engineering New Zealand through the Seismic Risk Working Group, and I'll talk to you a bit more about what they're doing in a moment, to assess what sort of changes might be needed in our building standards and how this might affect the regulatory system. And for the seismic assessment of existing buildings, we're working with the technical societies to determine what possible changes might be necessary in terms of hazard used in seismic assessments. But in the meantime, it is wholly appropriate to continue using 1170.5 for all seismic assessments. There is no plans to change the earthquake-prone building system. Okay? But we also really encourage you, and the fact that you're here today at this seminar and you're online for this seminar means that you're aware of this good guidance that's been put out by or you're interested at least in this good guidance that's been put out by the technical societies, the earthquake design for uncertainty. And we encourage you to follow the good guidance in that document that makes a building, if you follow these procedures, robust despite the uncertainty that we have in the hazard that building is going to face. Okay. MB is working on several strands of work that are going to contribute to answering some of these questions. And we organize this in the form of what we call our seismic work program. The National Seismic Hazard Model is a key input to that. And then we sort of break that into two streams. One, the existing building stream, and one, the new building stream. That existing building stream is broken down into a sub-theme of the stewardship of specifically the earthquake-prone building system. And then we've got a stream of work that relates to all those other existing buildings that don't fall into that earthquake-prone basket. All right. But what we're really here to talk about today is the new buildings, and I want to highlight in particular the work being done under the B1 VM1 update project in collaboration with Engineering New Zealand. So let me jump into that. So this is work that's being done, led by the Seismic Risk Working Group with the members listed there. And it's ongoing work. So what I'm going to show you here is sort of draft and subject to change, but I'd like to show you a little bit about where things are going. There are going to be two main outputs from this work. Phase one focuses on this elastic design spectrum, really focuses on how do we bring the outputs of the National Seismic Hazard Model into design. And our plan is to release this in collaboration with Standards New Zealand as a form of a pre-standard, if you will, okay, by middle of next year, with the idea of getting input from you, the engineering community, and then to be consulted on in due course for a future building code update. Okay, but we anticipate having something on the street for you to look at and respond to by middle of next year. Phase two is going to focus on aspects beyond just simply the design spectrum, but more holistically, how do we approach seismic design? And again, expect to provide a draft of that by the end of 2024 to MB, which would be released probably in a similar manner subsequently. Okay, but please note, dates subject to change. This is difficult material. These are difficult questions to overcome. And we're not going to release something unless we have a strong technical basis for that material. Okay, so it depends on us arriving at technical consensus on a proposal. In terms of the process from when MB receives or how this building code update happens, there are many steps in this process, okay? And in terms of this phase one, we're really in the middle of the develop arrow there today. And that's the work being done by the Seismic Risk Working Group. But there's a lot more stages that happen after that. This is something I'm learning in this new role I'm in with MB. It's complex. And each one of these stages, the pre-consultation, the consultation, the submissions analysis, the publication, each one of those stages takes a minimum of about 2 months or so in the best of times. And these are complex changes, so maybe a bit more. So please bear with us as we try to push these changes through as efficiently as possible, while still giving enough time for good feedback from all of you. Okay, so what has this B1 VM1 project been doing? We've been looking at the first early results of the National Seismic Hazard Model and now the final results, and thinking about some of these questions. What should the intensity of the design spectrum be? What should the shape of that design spectrum be? What are the site classes in relation to VS30? How should one be measuring VS30? What sort of geotechnical provisions do we now need to implement into 1170.5? Those are probably all going to be in the form of commentary, so I won't be going through those in any detail here today. And then finally, a few changes to some design provisions relating to possibly ratcheting and parts and components and rocking. Okay, so let me, I gotta have that disclaimer, draft still in development. So let me just go through a few of these, and I'm gonna start with the shape of the spectrum we've talked about a few times. We talked about the fact that, that you have different shapes of spectra in, say, Auckland as you do in Wellington because of the intensity of the shaking in Wellington. That this difference really is not represented by our current 1170.5 spectrum. And so one idea is to actually represent that change in the shape of the spectrum by actually specifying 3 parameters, not just a Z value, but a PGA value, a top of the spectrum, and a corner period. And with that, we're actually able to reasonably represent that changing shape of the spectrum as the intensity changes. So that's one thing that's under consideration. Again, draft still in development. Then we need to think about what's the intensity that we want to design for. Okay, and here it's important to remember that while we may design for 1 point, we expect performance well beyond that point, good performance well beyond that point. And I like to reinforce this with Rob Jury's rainbow diagram, as I like to call it. I know this is for existing buildings, but if I pick off this point over here for a new building, if you will, ULS 100% MBS, that's what we design at, right? But these colors here represent the fact that we don't expect really bad things to happen, red, until considerably larger than ULS, okay? And the fact that these colors are blended is quite important. We don't really know exactly where this is going to happen. There's just an increased probability that bad things are going to happen as you go to larger and larger shaking. So we need to represent that in some way. Well, this is challenging, but it's a real factor that we need to consider, because if we look at the hazard curve that represents the hazard for all ground shaking levels, for a single site, this is the same site in Wellington, but for two different buildings, a short building with a period of 0.3 seconds, the orange curve, and a tall building with a period of 3 seconds, the blue curve. What we see is that if we normalize this hazard curve is representing the shaking intensity versus the probability of shaking. Okay, so this dashed line across here is at 1 in 500. That's usually our design value. But if we normalize based on that value, so we normalize the shaking intensity based on the value at 500, we see that the shaking intensity as you go to more rare events actually gets considerably stronger for that tall building compared to the short building, right? And if we think about Rob Jury's curve here, we need to take into consideration that bad things can happen out on those tails of that curve. So how do we do that? Well, we can represent that fading red color by thinking of a fragility curve. Okay, and that's the probability. Technically, this is the fragility curve for collapse, but I like to think of it as the fragility curve for bad things happening. Okay, so progressively, there's a higher probability of bad things happening as you go to larger and larger shaking. Okay, and then we can integrate those two together, take the probability of having that shaking with the probability of bad things happen given that shaking, and that gives us an assessment of the risk, the probability of that bad thing happening. Okay, and if we do that, we get this sort of distribution, or the area under that distribution is our risk. And clearly, the blue curve, the one for the tall building, actually has a higher risk than the short building, and somehow it feels like we should recognize that in our design, right? Maybe there should be an adjustment that takes into consideration this variation in risk. And so we're considering this. We're considering the possibility of taking our uniform hazard spectrum and multiplying it by what we're calling a notional risk factor, perhaps, that maybe varies by period and considers the fact that that short period building had lower risk than that long period building, and adjusting based on period. Okay, but in the end, it's still a simple base shear that you design for. Again, draft still in development. Site classification, we've already talked about this quite a bit, so I'll keep this short. Now we're looking to use VS30 because that's the parameter that links us to the National Seismic Hazard Model. But we recognize that the VS30s can range considerably within the C to D region. And so we're looking to maybe break that down into several subcategories. Then importantly is how you actually measure and get that VS30 value. And there are several different ways in which you can do that. But what's important to recognize is no matter which method you use to arrive at your VS30, there is uncertainty in that number. And so probably some bounding of that number and looking at what is the hazard that results, or what is the design value that results from that bounding will be necessary. Okay. Again, draft still in development. In the interest of time, I'm not going to go through these proposed changes on the design provisions, but as mentioned, there's consideration of changes around ratcheting to simplify the Amendment 1 provisions based on some good work by Greg McCrae here at the University of Canterbury. Some consideration of parts and components as well as possibly allowing for some rocking foundations for simple structures. These latter two are really considered in order to make design practical in light of the high seismic hazard that we're seeing out of the National Seismic Hazard Model. So there'll be bounds on where these can be applied, but giving us sort of practical design approaches for most buildings, or for some buildings. And in particular with the parts and components, thinking about trying to leverage some of the good work that's gone into, that's been done here at the University of Canterbury by Tim Sullivan and his students, as well as some good updates that have been seen in ASC 7 across in the US. All right, and I should say that really there's much more to come on his design provision side of things in phase 2. And really those changes are really going to be informed by what we're talking about here today, this Designing for Uncertainty advisory released by the technical societies. So a lot of these concepts that we're going to be talking about will feed into the deliberations during phase 2 and possibly into future provisions down the road. But I just want to leave you with a reminder that as of today, the National Seismic Hazard Model does not change the way we design and assess buildings. We're working on exactly what the National Seismic Hazard Model results mean for the future and for how we approach the building regulatory system. But again, encourage you to engage with and use this Designing for Uncertainty guidance. And with that, I will turn it over to Andy.
Cool. All right, thanks. Thanks a lot, Ken. Thanks, Jeff. I should probably stand a bit closer to the mic, shouldn't I? And thanks for the introduction, Leah. Jeff, as you mentioned, provided some input into the advisories, hence standing up here today. Quite a big group of contributors, bit of an interest of mine. I'm trying to find that seemingly impossible balance between performance and economy. Also representing NZSEE today, they're doing some quite interesting work in the space with their Resilient Buildings project, which I'll touch on briefly during the course of the talk as well. Right. So what's this part of the talk about? Well, it's really just to go through and add a bit of colour to the recent advisories that have been released as part of the intent. The first one that was released was back in August. The intent of it was sort of twofold. First of it was really genocide and isolation of the National Seismic Hazard Model, and it was just taking an opportunity to reiterate how important, as Paul Campbell had put it, what is really just fundamentally good earthquake engineering design. But it absolutely does take the opportunity to use the hazard model release and kind of treat that as a really tangible example of what kind of this uncertainty can look like in practice when we've actually got something sort of in front of us, which really highlights how much of that exists in our industry. The second guidance that was released, this was released coincident with the hazard model release itself, and it was really just a bit more blunt communication on what this means right now and what's ahead of us in the next few years. So we're going to give a bit more background to these advisories. I think the earthquake design for uncertainty document in particular is pretty light on the figures. So we'll show a few more pictures and talk about a few of those themes. It's to help keep engineers informed of MB's work program, much of which you've heard about just now, look ahead towards regulation changes, and yeah, as Ken said, start that consultation process and start you getting ready to contribute to that. First part of this talk, I have to disclaim, it's a bit of a scene setter, and some of the material is drawn from a talk that I gave at the recent NZSEE conference. So some of you may have seen some of this before. It's really to pull that full picture of the why to all this. B1 VM1 remains unchanged. Why do you keep saying that? focus on design, not design actions. Why do we keep saying that? Ultimately, it's about just giving information, lots of information to help you have good, easy, productive conversations with clients and make good decisions as we move through this period over the next few years. Uncertainty is just part of earthquake engineering. The geotechnical profession is pretty used to it. Structural engineers tend to find the concept a bit more challenging or at least inconveniencing, but we need to let it guide design a whole lot more. We've got limited understanding of the hazard we design for, and the understanding that we do have is often presented in probabilities that we struggle really to know what to do with. It's come a long way, and from the outside, I think the impressive presentation gives the impression of a maturing science. However, we're still dealing in a limited understanding of the major faults that changes with time. We infer how big earthquakes could be, how often they might occur, and usually in a given area, this is on a frequency far greater than our lifetime. This slide shows the known faults which underlie our modelling. A little over 20 years of progress from the 2002 model on which our current seismic loading standard was based, through to the most recent community fault model, which is one of the foundation pieces for the 2022 update. 0.2% annual probability of exceedance. What does that number mean to you? Where are we at on the clock? Then if that earthquake occurs, there's huge uncertainty in how much shaking it'll actually generate at the ground surface and how long it'll last. It's a colossal amount below the ground surface that we'll never know completely. All of this important work is going to continue. The way we describe earthquake hazard is going to change continually, improve, and fluctuate. Then the built environment itself. Uncertainty in the ground, the structures sitting on or founded in, how the ground itself responds and what this means for shaking and distortions that the building feels, and how the two interact. Certainly not an elastic system. We've got uncertainty in the strengths of materials and even more in their deformation capacities. Uncertainties in how a structure overall responds dynamically to the shaking, and into all those other secondary contortions that we might not necessarily model. This is a particularly simple and elegant illustration of uncertainties. David Hopkins helpfully forwarded a tidied up version with a few of the text scrawls overlain with some nice tidy text boxes, but I think I prefer the original. It's real structures, he said, designed and built that have to resist earthquake actions, not the theoretical models that we analyze. What David's shown on this diagram is a couple of calculation trajectories which sort of follow a path where vastly different, well, assumptions made can lead to a vastly different outcome. And although one way of interpreting this is to suggest that we should, we should go down all of these paths and all of these rabbit holes and analyze and bound for all these various assumptions that we make. And to an extent, that's true. To an extent, we'll do some of that as part of our work. But ultimately, what we come up with a design should really just be desensitized to some of these uncertainties. And hopefully, as we go through, you'll see that I think that's possible. Load resistance factor design. This is the current benchmark for delivering a safe design. We define an upper bound in our loads, a lower bound in our strengths, and we put factors on each side to get that unsafe area down to something that's good for us. For ordinary static design, failure is a practical impossibility for all practical purposes, unless something's gone quite spectacularly wrong. And forensics will tell us that it's usually a combination of things that go wrong to lead to an actual failure. Gross overload well outside the intended use, dilapidation, design error, construction defect, again on a gross scale, and none necessarily related specifically to this image, which is more for context. So yes, failures occur, but there's a high level of control. We've got some influence over the loading, we know what's possible, and whether we choose to or not, we can have some control over it, and it's in our power to manage. Compare this with seismic design. Load and resistance factor design does remain the benchmark, but the loading is completely beyond our control, and let alone our ability to even quantify it. The considerable uncertainty needs a different mindset. This diagram is similar to the last one, but in cumulative probability. The red is an example hazard curve taken straight out of 1170. And the blue shows an IL2 structure designed for that hazard. Shows generically the increasing likelihood of collapse, just as Ken described it, as we push that demand further and further out. We select a return period for design. We pair that with an ultimate capacity, and we use resistance factors and safety factors, and we have some margins in our deformation limits. So these give us some sense of the reliability that we get at ultimate limit state, very high levels of reliability. But with such considerable uncertainty that we don't really know for sure how much of a margin exists and how to really represent that diagrammatically. And in some cases, that point of collapse is going to be well beyond our ultimate calculated capacity for a variety of reasons. I certainly would not be opening that roller shutter door if it was me. Our first most basic objective as engineers is collapse. It's collapse that we're interested in. It's not the only thing that we're interested in, but it's kind of one of the fundamental things that we are looking to, deal with at all costs. And so in this particular set of slides, I am talking about the life safety objective and the collapse resistance of new designs. We don't have really any interest at that point whether an ultimate capacity is exceeded or not. We're using it as a proxy to try and avoid collapse. And it's the overlap down here, which is what we're trying to minimize to get close to what we think society will tolerate as a collapse risk. And it's certainly a lot lower than 10% in 50 years. This is, of course, the cornerstone of modern seismic design. Robustness, ductility, redundancy, and a different use of the term flatten the curve. Although standing up here now, it's the COVID reference is kind of long since passed on that one. An essential ingredient for earthquake engineering design. Forget your 5% rounding. A fragile building, the dotted line, that is, with disproportionate sensitivity or step change is vulnerable. The 10% plus drift angle on that building before isn't going to do all that much for you if it's concentrated in a single story. On the other hand, we tend to underestimate the real displacement capacity of well-configured and ductile buildings. They're largely insensitive to a bit more or less shaking. A building with the same ultimate capacity, and these two buildings have that, but which doesn't have that fundamental ingredient, could easily be 10 or 100 times more likely to actually collapse from an earthquake than one which does. Instead of plotting uncertainty bands, if we just test a notional 50% increase in the hazard curve, the acceptability of this fragile design would really be called into question. Whereas I don't think it overreaches to say that for the ductile design, collapse remains a practical impossibility. Unless we're straddling a 10-meter fault thrust or the hillside swamped it, then we're good. Our design processes hide away a lot of this uncertainty because the process that we use to get code compliance by comparison is pretty damn certain. Whether you subscribe to that 5% rule or not, the simple and necessary compliance test tends to overemphasize design forces at the expense of that key ingredient for earthquake engineering design, which is designing for uncertainty. So this, of course, we know, right? Uncertainty demands a certain engineering response. Ground shaking can't be controlled, but structural performance can be controlled. If graphs aren't your thing, then we can look at some evidence. Past failures have taught us that significant failures really occur because the ground shaking was a bit more than expected. In fact, if a big earthquake happens, we actually expect it to be larger than the design level for a number of buildings in that region. So you're hard pressed to even call it a contributing cause. Failures result from irregularities. This example is a torsional irregularity with severe amplification on that front corner. It could be a lack of stable behavior without capacity design. In this case, we've got a severe lack of low path in the wall collectors. And as well as that, a lack of deformation compatibility and robustness in the attempted retrofit. And in this case, also a lack of deformation compatibility and tying to minimize the consequences. Here in the Kakura earthquake, see what's left behind and what's left collapsed onto the floor below. Although a relatively flexible building, this is fundamentally a deformation compatibility issue. Although there is a basic load path problem with the loop bar detail, fundamentally a deformation compatibility problem here. Significant configuration irregularities, both in the obvious change in structural form, but also significantly unbalanced lateral strength. Even the irregularities and transfers we think we can design through are problematic. Clever bespoke approaches have varied success. There aren't standard methods. The best engineering and intentions and most rigorous analysis just too often miss the mark. These things just perform in ways we just don't expect, or we make mistakes. And I hope this isn't too far of an overreach of David Hopkins' uncertainty, but the uncertainty is just so much bigger for an irregular structure, almost beyond what good design can deal with properly. And there's little that can be done about that. Well-conceived, regular structures with clear load paths just perform better. Applying a set of design actions, sizing up and reinforcing some elements, that's not a seismic design. Well, not yet anyway. This is a seismic design. And I'll put on the slide a few examples of some designs that Mick would happily pull out of his back pocket. We have a doubly reinforced wall, a precast wall with properly confined drossbacks. And here's a test image from a research paper illustrating why we do that. The image on the left without confinement, and there are similar images from real walls following the Canterbury earthquakes. On the bottom right, a ductile moment frame connection ensures stable beam yielding and a nice strong column. A simple standard connection type that any multi-story design should use. On the top right, a rod bracing connection, full capacity, dynamically tested, well noted with a simple direct load path into the foundation element, engaging the web and the base plate. It's all pretty simple stuff. I promise this is the only slide with the extra theatrics, but it's done for a reason. If there's anything that you take away from today, any sort of single message, then this should be it. Yeah, Australian hero teaching a few humble Kiwis how to do seismic design. So these concepts form the background to this document. The concepts are sound, they're not new. This new hazard model release is really just a great opportunity to highlight the relevance of them. As you've heard from Ken, until B1 VM1 is updated, there's no change to minimum regulatory requirements for building design. But if there's any question as to what developers can do in light of this new information, then this is the recommended answer. This is one of the outtakes which reinforces that even before B1 VM1 is updated, even if engineers are continuing to use 1170.5 loadings with the geotechnical practice modules, these design principles can have a very large influence on actually achieving the real performance that we want. And it's so much more likely that in 5, 10, or even 50 years' time, we'll look back and be just as happy with that expected performance. And that's got commercial value. So we'll return to some of the detail of these a little bit later in the seminar. But now we'll move into the next part session, which starts to look specifically at the 22 hazard model, what it is, what it means, and a bit more on that building code revision process. Ken and I, in coordinating our slides, we did decide to include quite a bit of an overlapping material here, thinking it would be useful to kind of build that complete picture, even if it's some of its similar messages with a slightly different set of words. So what is a hazard model? We look at the plate boundary, we look at all our known active faults, and we decide how big and how often we think they'll go. And then if you can see the faint blue outline underneath these zones on the zone diagram, we do the same with all the faults not yet discovered or not yet in existence. We make some allowance for those, and we do a similar thing. For every one of those, we estimate how much shaking they'd cause if they went. And there's a big roll of the dice there too, because there's huge uncertainty bands in that. It's a very hard thing to estimate. We multiply the two together, add it all up, and all of a sudden, with a lot of calculation, we have a hazard model. We can now see how likely it is that within our lifetime, or our notional lifetime, a certain level of shaking might be exceeded. So there's a few different ways that we can use this information or interpret this information, and one is through maps like you see here, and another is through a hazard curve. This is an example from a Wellington site. It's for peak ground acceleration, and as we increase that reference PGA, we see that it becomes less and less likely that an event in our lifetime, or ever for that matter, would exceed that reference PGA. And if we pick a probability level of interest, say that the 10% in 50 years, or that 500-year return period value that we're used to, and combine hazard curves together, then we get something much more familiar looking, a uniform hazard spectrum. This is usually far more interesting to us as engineers, or at least structural engineers. For different types of idealized buildings, stiff or flexible, it tells us the global peak acceleration, the base shear, that corresponds to that selected probability of exceedance. So there are some limitations to this. It's for a purely elastic single degree of freedom oscillator. Buildings aren't perfectly elastic. The good ones at least have some give and ductility. And foundations certainly aren't elastic. And few buildings are a single mass. They might be multi-story or flexible in plan. But with a few simplifying assumptions, this diagram can still tell us an awful lot. But there's something that it doesn't tell us, something which is absolutely fundamental, and it's this. And apologies to everyone who thinks that this is stating the blatantly obvious, but someone has to decide what that number should be, and it's not a solely engineering decision. We're very used to this idea of using a 500-year return period for our importance level 2 designs, but it's nothing real. It's a completely implicit value that is all part of the construct for trying to avoid collapse. But assuming that is decided, let's continue the comparison. Left is a design spectrum from 1170.5. The scale's a little bit awkward because I did try and match them, so it's a little bit cramped. Aside from the fact that 1170.5 is developed off the O2 model, the main point here is that it's no longer a true uniform hazard spectrum. Got smoothing and averaging and assumptions around site class and return period factors, all to help its ease of use. And there's definitely a few gives and takes that come with that, as Ken showed. But even if we did try and transplant a true UHS into our standard, there's other differences. Why does the design spectrum truncate the short periods? How is it decided where to draw that line? Other adjustments are sometimes made to reflect geotechnical and structural behaviour and to factor in risk. And Ken's already touched on that, and a bit more on that again soon. But it would also be strange if a modern approach to seismic design involved basically hoping that an earthquake doesn't happen nearby. And yet in the lower seismic zones, that's exactly what can result from selecting a 500-year return period for design. This is an Auckland example, albeit it's a few years old, and I'm not going to explain the slide fully. Suffice to say that historically in New Zealand, a lower limit Z value has been defined, 0.13 in Auckland, and it's based on a reasonable scenario of a severe earthquake reasonably close by. It intends to force that level of robustness to avoid one of those peculiar and slightly uncomfortable pitfalls of probabilistic analysis. And looking at the 22 model, thank goodness we did that. And thus it follows that the hazard model itself is not a design standard. It doesn't mean that it can't be used, it can. And Shord will talk more about this soon, but it's important to recognize this. Having this information so easily accessible is absolutely fantastic. It's pretty amazing to be able to interact with it so easily. Even, you know, Ken's already talked about the world-class research. The portal itself is world-class. Even in its initial release with pre-populated data, there's a lot of information there and more features on the way. Yeah, very usable resource and excellently presented. So Shord is going to spend a few moments now talking about a few subtleties with its use, particularly as much of it, as Ken's noted already, comes down to site classification.
All right, so I had a chance to have a play with the portal, and as Ken has alluded to, it's got site effects built in with the VS30 parameter is the main thing you put in, other than location and the probability of exceedance that you're looking for, and then you can get the spectra coming out. I just had to play in different areas because, you know, VS30, if that's a key input, yeah, that drives the intensity for different areas. Then, you know, if it's an unknown, we don't have it, we might, you know, as engineers tend to have an approach of, I'll just pick a conservative number. You know, if an unknown, I'll just be a bit conservative. Well, it's interesting. In Tauranga, a conservative number may be a low VS30 if you're looking at a high frequency end of the range like PGA. But in Wellington, it's actually a you know, a much higher VS30 number. At a different spectral period, it might be the other way around, so there's crossover. So what's conservative and what's unconservative really depends on where you are. If I start looking at Tauranga a bit more and then look at different probabilities of exceedance, the 2% being sort of closer to the 1 in 2,500 and the 40% probability of exceedance about the 1 in 100 gives you sort of sense of equivalence. What we can basically see is that the the lower VS30 numbers are driving higher intensities, but not so much at the larger or lower probabilities of exceedance. And Wellington goes the other way. So the intensities that we can get are dependent on VS30. It is sensitive, and so we need to put a good VS30 number in. We can't just take a guess at it. So what does a good VS30 classification look like? Well, it's got to start with some robust seismic testing. But it could do the most perfect measurements in the world and still land in exactly the wrong place, because we need to consider the geology, the vertical stratigraphy, the horizontal stratigraphy and changes, spatial variability, and we need to think about how the ground behaves. Getting a location-specific VS30 may not actually then give us a representative VS30 of site behavior for ground motions, and I'll go into that soon. I'll make some comments about ground improvement and also non-linear soil behavior, and just some of the things we need to think about the limitations of VS30. So VS30 profiles, they can be inferred from boreholes and CPTs, and if we then infer them, we could then go on to average the shear wave velocity over the top 30 meters and move on to estimate a VS30 number. But interpreting a shear wave velocity from a CPT, for example, in pumice or aged soils, can lead us into a different place than the actual VS, because that would be in the ground because they're different. Also, there are some techniques out there in the published literature that are proposed on how shorter CPTs and boreholes can be used to infer VS30. That might work in some areas and some geologies, but certainly been looking at the numbers and actual measured VS30s versus what can using those techniques to extrapolate, and we get quite different numbers. So a lot of caution needs to be applied if we're inferring. We can get VS profiles from robust seismic testing. Methods include downhole seismic CPTs, crosshole, direct push crosshole. Those are all invasive methods, and they're all well detailed in module 2 and the accompanying document. There's also non-invasive methods of MASW, SR, H/V. They all have strengths and they all have limitations. If you've got a highly stratified soil of stiff and non-stiff soil layers, and you're doing crosshole testing, you'll completely overestimate the shear wave velocity of the site and miss all the non-stiff soil layers, how the shear waves will jump between the two. If you've got vertical stratigraphy, doing a downhole based method could completely overestimate. So it is really important to understand the strengths and limitations. apply good test methods. You know, if you're doing a downhole, your seismic CPT, and it's a pseudo interval or a true interval, the offsets of the block are really important. And a lot of that detail is captured in module 2. And I'm not going to go into all the details now. Suffice to say that, you know, this testing can be done really well, and you can get good answers out. It can be done very poorly, and you can get, you know, nonsense answers coming out. And if we plug those in, we can get intensities that are way off the mark. It's always good practice when we do get from seismic testing shear wave velocity profiles from which we derive VS30 numbers, to compare that back to boreholes, SPT, CPT. I've seen some results come out where shear wave velocities were reported on being sort of 400 or 500 meters a second. Seemed a little bit odd for the location, and then I asked to sort of have a look at the CPTs. It was a seismic CPT, and the CPT had a QC values of 5 MPa the whole way down. Suggested that that was either a very special material that had never come across before, or that there might be some type of error. After a bit of investigation and back and forth, it was concluded that it was an error. So apply common sense. So just assuming that we've got a good, robust test method that's been applied, we understand the limitations, we've applied the right methods for the site, and we get a good VS profile, we can then go on to calculate a good VS30. I'm showing here 2 soil profiles, or 2 VS profiles, that both calculate the same VS30. One would be of a site where the soil is progressively becoming stiffer with depth. And that is the typical soil profile that, you know, has been derived or used for all the VS, so for all the GMPEs that inform the seismic hazard model. But, you know, there are a lot of cases, you know, or exceptions where we have, for example, stiff soils overlying alluvium, such as basalt flows overlying alluvium in Auckland and Tauranga. There could be ignimbrites, or, you know, very stiff ashes overlying uncemented loose sands. And in Taupo area, I've sort of seen those where all of a sudden the VS profile becomes inverted. When we start to think about the ground surface response of the orange profile and the blue profile, they will be quite different. There'll be a lot more damping of the high frequency content with the orange one, and lot you know, stronger you know, shaking intensity at the higher periods for the orange. So VS30 is not a good representative characteristic for the orange site. So you can calculate a number robustly, but is it actually going to be a meaningful number to plug in into that hazard model to get out shaking intensities? Or is that sort of immediately got to raise some alarm bells and sort of say, well, there's a lot of uncertainty there. If you actually want to get a better handle of it, you know, for the orange one, you might need to actually consider doing a seismic site response. All right, let's just consider horizontal you know, changes in spatial variability. The map on the left there, you know, is an example of showing the thickness of overlying material on top of basalt, with the basalt is variable in, you know, its depth. Some areas it's shallower, some areas it's deeper. You've got a material overlying. Now, you could do a point location measurement, get a VS profile at that point location, and we could turn that into a VS30 map that would show a lot of spatial variability on that VS30. But where we've got, you know, changes occurring within close proximity of each other, are we really going to get different ground motions at 2 different point locations in close proximity to each other? No, it's going to behave as a system. This whole soil system is going to move together. Yes, you will get, you know, that they will influence each other. Likewise, when we have spatial variability in density, for example, you know, we will get softer, you know, looser pockets of material. You know, for example, in fills, you know, surrounded by dense material, Again, are we really going to get different ground motions at one point and then sort of move 10 meters or 20 meters across and get different ground motions at the ground surface? Or is the system going to be working together as a whole? So effectively here I've simplified that into a picture of different soil columns. The blue ones might be a higher VS30. The orange one might be a lower VS30 because all of a sudden it's a, in an infill, incised channel, either side of that where the bedrock is shallower, or it could be a looser pocket of material. This system is going to behave together as a whole, and everything will be influencing each other. So the ground surface motions will start to sort of spatially average. So a location specific VS30 may not actually be the right thing to put in. You need a site VS30. Likewise, this could be a denser material. I've seen some reports where ground improvements have been undertaken, and as a result of doing ground improvements, it's been argued that because it's stiffer now, that they can change the get a higher VS30 and hence change the site classifications. Well, if this ground improvement is relatively narrow in extent, say 30 or 40 meters across, and we've got soft soils on either side, everything's going to flock together, move together, push and pull. And that stiffer material is not going to behave as a stiff soil site. It's going to be some type of composite of between, because the soils either side of that will be pushing and pulling that. Again, there'll be some type of averaging. Then there is also another common case of, within valleys. In the Hutt Valley, for example, on one side, you get this sort of basement bedrock wall coming up steeply. You'll have the valley infilled with alluvium. And so you could get a measurement, within the valley that is giving you a sort of a VS30. But when the earthquake shaking occurs, you've got the bedrock from beneath shaking that, as well as the bedrock shaking the sides. And so the ground motions that you might get several hundred meters back, well and truly into the valley, may be more representative of the VS30 of the soft material, but sort of as you approach closer to the sides of the valley, you're going to get quite different motions. And again, there is uncertainty. You could consider doing a 2D seismic site response to better quantify that, but it just really is, care needs to be taken. And for structural engineers, you do need to sort of consult with engineering, geotechnical engineer to sort of understand the appropriateness of a VS30 number. And finally, you need to consider nonlinear soil behaviour. I've just pulled up the example here of the REHS strong motion station in Christchurch and Durham Street, and got the ground motion from the February 22nd earthquake, showing on the two components of shaking, the acceleration time histories, top graph and the third graph down, and then double integrated to show the displacement time histories. Liquefaction occurred at that strong motion station, as well as quite a number of other strong motion stations in the area. And at time equals 15 seconds there is a distinct phase change that occurred. Frequency dropped, frequency change, the amplitudes of the displacement still stayed large. Professor Steve Kramer sort of looked at that with the Stockwell transformations, and really that's the point at which liquefaction triggered. Before that, you get a much higher frequency content, shaking intensity, and after that point, you get an amplification at the 3 seconds. So when we look at the spectral period with that bump in there, a lot of that bump, a lot of contribution to that bump is coming from a phase change that's occurring, or a nonlinear behavior that's occurring at some point during the shaking. So if you've got a site that's going to liquefy or going to exhibit, nonlinear behaviors, what VS30 do we take? Do we take the VS30 before that change occurred, or after that change occurred, or some type of hybrid? Again, uncertainties. You again could consider doing a seismic site response with effective stress analyses to help quantify those effects or bound the problem. Just picking back up on Ken's slide, there's plenty of methods, but it all needs a very good dose of judgment. And, there is uncertainty, and that needs to be bounded. It is an important parameter because as I showed earlier, it does affect the shaking intensities that one would use for design. But because of the uncertainties, it's not just a single number. We need to sort of bound that, and that will require quite a bit of expert input. Right.
As I said before, data very openly available, very accessible, great to be able to interact with it. But obviously to actually use it, we do need a bit of expertise, and it's important to stay within our competence, both in terms of the geotechnical engineering aspects, which Sean's just covered, but also for, some projects, particularly special projects, which using, more advanced types of analysis, then engineering and seismology input can be really important as well to understand some of the subtleties around how the data actually comes out raw and what that might mean for the way in which you're using it. So if we're saying the 2022 model is not a design standard, but it is being used to inform building regulations, then the question that obviously comes next is, might we not want to use this best information available to us to inform my design? And the answer to that is absolutely yes. Yes, we can, and we should use the best knowledge available to us. But to answer this question properly, we need to look back at the processes used to develop building regs, including some international precedent. And there's a couple of things to point out. So first of all, it's been 20 years since a major revision of our seismic loading standard. Work in the past 5 to 10 years has heavily foreshadowed some of these trends that we're seeing, but our design standards have remained static. So purely given the time that's gone by, it's little surprise that the new science is painting a bit of a different picture and is coming as a little bit of a jolt to the system. Secondly, we've also had significant earthquakes in this time, and as a result, learn a lot about the sort of outcomes that we're prepared to tolerate and those that we're not. Possibly we've also learned a bit about what we might be prepared to invest in preparation prior to an event and what we're not. So we definitely should stop, think, and ask a few questions before we simply plug and play. Given what we've learned about our risk appetite, is there a different way we should be using this hazard information than we have before? So yes, these questions are being asked and answered, and this broadly describes how that's done. This is our building code triangle, and it fascinates me that it's me that's showing this instead of Ken. Ken told me that since joining NB, he's learned that every single presentation as an NB employee needs to include the building code triangle. So this is the regulatory framework, and if we go right up to the top to our building regulations and our building code, this is what we find. Our building code objectives. It's interesting, they talk about risk effectively, injury or loss of amenity from structural collapse or structural behavior, and they say absolutely nothing about design return periods. Risk is a combination of likelihood and consequence, and yet they don't actually tell us how much risk to accept either. Standards committees need to make some decisions, and to do that, they need some inputs. One of those obviously is the hazard. This tells us the likelihood of certain levels of shaking. And it also tells us something that wasn't so visible to us before, and that's the uncertainty in the hazard. So the middle line there represents the mean, and that's the current best estimate, or maybe not necessarily the best estimate, but the middle of a whole lot of estimates that represent all the different models and variabilities and things that are considered in the makeup of this model. And then the solid shading is the 80% confidence bounds, and outside that, the 99%. But the most practical way that I can think to describe the bounds shown is that it attempts to represent that learning process. As science continues to develop, we might find evidence that skews that best estimate or that middle estimate one way or the other. Maybe it's new faults, maybe it's better understanding of amplification effects in sedimentary basins. Maybe it's just loads more data from real events and some of it local. Theoretically, at least, these lines do help to set a bit of expectation there in terms of, where that knowledge in the future might sort of land or sort of trend towards. But the reality is that sometimes new science teaches us things about what we don't know too, confronting things. And so maybe those lines can shift as well. In practical terms, science can helpfully give us a range of plausible shaking intensities and an indication of likelihood, but ultimately we'll never know the earthquake that a given design will ultimately need to face. We'll continue to find ways to select and constrain models to better fit the real underlying phenomena that we're always learning more about. And the way that we design should reflect this learning process and the uncertainty that we live with. If we're expecting our understanding to change, then our design process should accommodate for that. So this key message should highlight how important our material design standards are in working with our loading standards to work together to deliver structural safety. And interesting, it also highlights how they can be used to lessen the need to continually change and tweak our design loads. And although this point jumps ahead a little bit, the phase 2 work alluded to by Ken on our building design processes is a very important part of all this work. The next set of inputs are broadly grouped under this term tolerable impacts. And it really comes down to these two questions. There's a significant project that NZSEE are leading at the moment called the Resilient Buildings Project. It's predominantly a social science research project led by NZSEE with funding and support from Tokatu Ake EQC. And this is a wee diagram that the team put together to talk about tolerable impacts. And I should thank Shannon Abling for providing these slides, these next few slides. Shows the idea of this trade-off zone where the cost to community today to prepare is balanced against the impacts of an event. These slides will be available later, so I'm going to go through quicker than you can read. It's really only a bit of visibility into the back workings that we need for today. And it's really hard, this balance, because earthquakes are rare events. And yet if they do occur, the impacts can be devastating and lasting. So naturally, we're going to look to invest in those things which cost relatively little, but have big impacts on performance. Working out what impacts a community can tolerate, and that's not easy, but that allows us to turn that into building performance terms and ultimately into design standards. These are a few snippets from the Stage 2 report, which makes for some interesting reflections. The project thus far has found that life safety does remain people's first concern. It's held above all else. People just expect safe buildings, but social and economic recovery soon become pretty important, and risk tolerance in that regard is actually quite variable across different types of communities, whether they be well connected or geographically isolated, whether they're high or low density living, and so on. This town map exercise is an example of one of the ways that information was gathered. Diverse mix of participants from all walks of life were asked to spend their limited and highly prized tiles on where they wanted the most investment prioritized prior to an event. Similar sorts of activities were used to compile this diagram, which presents a broad cross-section of the public's views on tolerable timeframes along that top axis there for functional recovery. And they were encouraged as much as possible to be realistic about it. What's interesting about this one is the comparison of residential apartments versus commercial office buildings. Naturally, and it's kind of obvious when you think about it, but there's a far greater impetus for housing to remain livable and safe and be back near to full function within a shorter time frame as possible. Particularly an issue for multi-unit residential. The research has also noted the relevance of this research being carried out in the wake of a global pandemic, and so likely some pretty fresh reflection on what you truly can and can't live without. I also find it a little interesting that the restaurant pub functional after a day, and maybe that's for everyone just to take it all in, relax and empty the kegs, and then, but it's okay, another 12 months until we're back open. So prompts some interesting reflection on whether our importance levels are cut quite right. Then we need to look at building performance, next set of inputs. And recall how we compared two buildings designed for the same ultimate design action, one well configured and the other not. The way we design has so much influence on the actual performance. Ken showed how even a design loading standard can account for this too by risk adjustment. And these standards can work closely together. even if we choose to continue using that 5-year term period event for our ULS design point for IL2, we can factor in the way buildings truly perform. And if we chose to, we could choose to reward well-designed buildings better than we currently do. In the US, a change was made to risk-adjusted hazard back in their 2010 design action standard. They call it risk-targeted design actions, and a paper was presented at the 2021 conference exploring how it could apply to New Zealand buildings, and you've heard more about the more recent proposals today. There is a bit complicated for sure, but it does make sense, and it's all done for us, so our design process can be kept simple. So that hasn't been done explicitly in New Zealand before, but there are other more implicit forms of risk adjustment that have, for example, that short period truncation. Short period buildings in particular can see proportionately larger benefits from various types of soil damping that come about from soil structure interaction. Rather than carry out complicated analysis again and again on every project, a very simple adjustment by the experts can save us all the trouble and get us a similar outcome. And this is one of the, not the only, but one of the reasons that we see this sort of adjustment quite clearly applied to our design spectra. So scientists define the hazard, engineers help fold in building and geotechnical behaviour, describe the risks. Society decides what level of risk to accept. And together we kind of feed that back up into our performance criteria and then filter it down through our design standards. So the summary points out of all that is simply to reiterate that the future building code provisions aren't necessarily exactly what we're seeing in this 22 hazard model. The changes are enough of a jolt that we do need to step back and ask that big question. We do need to review those risk settings. But on a simpler and more practical level, we really just need to recognise that to actually manage risk, we should be focused on design configuration foremost. I think we'd planned to take a 5 or 10 minute break now, Jeff. Cool, okay, we'll get underway again. And to start the last session, just a summary, bit of a wrap up of some of these key messages. And this comes straight from the front page of the interim guidance recently released. And just reiterating the thing that you've heard many, many times now, that until the minimum compliance pathways change, B1 VM1 is still the minimum. But that third bullet point is important. It is recommended that engineers at least discuss the existence of this new information with clients. They do deserve to know. Ultimately, the decision will rest in their hands, but they deserve to at least be brought up to speed on the fact that there is some new information out there. It has been well publicised, or at least it was in the week of the release, and so many of those that are interested will have picked up on it. They should be clear that the hazard model is not a design standard, and that the first look at proposed changes we might start to see as early as mid next year. And of course that any proposed changes will be consulted. And it's also an opportunity to start to engage that wider industry to be part of this consultation process. We get the building code framework and regs that we deserve. And so it's important that we do engage with those, through our networks that are going to be potentially significantly impacted by some of these upcoming changes, and we want them to be able to have their say and be prepared to come along for that ride. Although this next slide applies probably to a very small fraction of our projects, it's nonetheless important to answer, and that is, can I use the 22 hazard model for new design to meet the building code? And the simple answer is yes. Much as we have in the past, through an alternative solution, used a site-specific hazard study to demonstrate compliance with the building code, that compliance pathway still exists. Ultimately, that decision rests with the consenting authority, but there's a pretty well-worn path there. But that second bullet, again, users and clients do need to be aware that it's not future-proofing. It doesn't equal the new code provisions. And it is recommended that if clients are actually interested to, well, of course they are, to achieve better than code performance, then any increased loading that project teams do decide to include should be done in conjunction with, and certainly not instead of, some of these fundamental engineering principles being applied. In this next subsection, Short and I are going to spend a little bit of time covering the application, which is Paul Campbell again succinctly put it, it's really a little more than fundamentally good design. Mark Willard is going to follow up soon with a further case example of sorts, describing the Ministry of Education's requirements for their stuff. They're living and breathing this stuff, so it should be a really nice, tangible example of how this plays out in practice. New Zealand's building code standards or building standards deliver a good level of structural safety, but they don't necessarily deliver the robust, ductile and regular design consistently that's been described above. They do rely to a degree on our assessment of the loading being about right. The current life safety focus also leaves New Zealand a little bit exposed to difficult and long economic recoveries. And that applies both to a building by building level as well as across a community. So although we know that some clients may prefer to drive minimum requirements for a minimum first cost, there are many who have a broader interest in building performance and some who have tangible market value tied up in measurable seismic performance. So there's certainly no need for unnecessary concern or overreaction. But again, our clients should at least be given the opportunity to understand that this new information exists, that MB plans to work through some building regulation changes. Should they wish to keep abreast of it, there is something that can be done now, and that involves following these recommendations. Some of the specifics do go a little bit further than current design standards do. And the reason for this is to make sure that we remain focused on ensuring good behaviour from buildings. 8 recommendations in total, the first of which is peer review. And that's of course because the outcomes that we see are far better when we work together. So although there are a few specific points in the recommendations, it's mainly high level guiding principles. But early last week, SESOC issued version 11 of its interim design guidance. This forthcoming update was alluded to in the Design for Uncertainty advisory, and that work's now complete. It's through its reviews, and this document's now available to download from the SESOC website. It's a much longer document, 81 pages of PDF, and so it does get into some of that really helpful detail of how this stuff can actually be applied. So it should be an invaluable resource. Many of you, particularly in this audience, will intimately know the history of this document, but it was a document that was produced in the wake of the Canterbury earthquakes. It was put together to help support the rebuild by immediately taking some of the very real learnings from the earthquakes and get them into practice before they were sort of mopped up and picked up by the building code and building standard updates in the coming years. As we know, there is a lag. There is a long lag between good practice learnings, best practice being absorbed into the building code framework. In 2019, version 10 of that document was released, and largely that was to strike out a bunch of the material that had at that stage been incorporated into the verification methods. And this version 11 is a fairly substantial review, and it goes into a bit more detail, and it really acts to support and sit in behind this earthquake design for uncertainty document and provide some of that key detail. It has 3 levels of recommendation. First of those is a verification method requirement, which is actually not so much a recommendation. It's really just clarifying requirements that do exist, but perhaps there's a need to emphasize or clarify the meaning slightly, or maybe we see that it's not something which is being applied so well in practice, and so it deserves a bit of emphasis to make sure that people understand that there is an important provision there that is important for performance that needs to be applied. In the middle, we have a SESOC recommendation, and these are better practice or best practice design and detailing recommendations. The third there is, there were a few of these in the prior edition, but there are now a lot more. There is a low damage design guidelines project that we hope to see recommencing soon. And that goes into a lot more detail around what is low damage design, what is repairability, how do we, you know, avoid what we saw in the aftermath of Christchurch with so many buildings being demolished. In the interim though, these recommendations are simple, practical, often simple things that can be done, which go a long way to minimizing damage and enabling, you know, repairability and a return to functionality. And so applying and following these recommendations will go a long way towards, you know, reducing damage in our designs. So for low rise or simpler structures, it's robustness, low path deformation compatibility, tying and avoiding brittle behaviors. For more significant structures, it's the same, but with deliberately controlled ductile global behaviors through capacity design. It's the stuff that you should be able to draw with a Magnum Sharpie. And I planted this slide here, which just gives a good collection of the range of things which our designs need to deal with, which are not just theoretical, but are very real examples of how deformation compatibility is so important to get good real world performance. Right, at this point, Sean and I are going to lead into an example. It's a fairly simple example, but nonetheless, it's at least gives you some insight into the way that these recommendations can be applied in practice.
So as we lead into the example, you know, for geotechnical, you know, considerations, often there is step change in ground behaviour. We don't sort of get a progressively degrading ground. You know, in the case of liquefaction, for example, you know, nothing happens up to a certain point. There's a certain shaking intensity where something starts to occur, and then very quickly with a little bit more shaking intensity, it's all on and sort of plateaus out again. So we need to consider the step change in ground behaviour, and you know, in some locations for some projects and in some shaking intensity zones, that step change could be occurring between SLS and ULS. And so the question that we do need to ask ourselves is ULS levels of damage acceptable to a client at return periods very much less than ULS? So we can easily, you know, to have a site, and you probably think of many here in Christchurch, where at SLS, levels of shaking, no liquefactions triggered, fine, happy building, no damage. At ULS levels of shaking, well, nothing's going to collapse, meet the objectives. Probably need to rebuild the building at ULS, you know, with those levels of deformation. But then, you know, what if at slightly higher shaking intensity, a little bit beyond SLS, all of a sudden you've got the same levels of damage than at ULS? Is that really what, you know, the clients are expecting? You know, and it's liquefaction as an example, but you can have slope failure. You know, so slopes that sort of create a building platform. You know, for liquefaction, we need to think more than just the triggering and settlement, but, you know, what's the implications of settlement? So we could design a robust foundation system that can be tolerant of differential settlement, but if the whole building platform goes down, you know, and it's then sitting below a minimum floor level and you start getting flood issues, and that's happened somewhere between SLS and ULS. What good is all that fancy engineering doing for us? You know, we've got differential settlements to consider, loss of bearing capacity. And in the first part of the example, we'll sort of more look at the differential settlements rather than the bearing capacity issues. And then when we come into lateral spread zones, there's stretch, but lateral spreading further contributes a lot of additional settlement and a lot of additional differential settlement. For some sites in lower seismic hazard zones in New Zealand, that step change might not be occurring between SLS and ULS, but might be occurring after ULS. Given all of the uncertainties that we've talked about, you know, and you know, if the shaking intensity was just a little bit more than a design ULS, and all of a sudden we get step change, if one allowed for the uncertainty, does it make sense if we just allowed for a little bit of uncertainty that we'd end up with a completely different building design than, you know, if we're designing based on a precise number at ULS? Wouldn't really. So we need to look beyond ULS, you know, and consider what happens there. We also need to consider the geotechnical uncertainty. Yes, there's the shaking uncertainty but it's also the geotechnical uncertainty, and I'll show that in an example now, and the consideration of other geohazards. Sometimes we got empirical formulations, we can get carried away with numbers and present answers in sort of 2 or 3 or 4 decimal places, when really we'd be lucky to actually present an answer and one significant figure with any level of confidence. Lateral spreading is a really good example of that. So I went on to the seismic hazard portal for Wellington. I went in over the weekend, picked the probability of 10% exceedance in 50 years, picked the VS30 of 250 meters a second, and got my shaking hazard curve coming out, and also got the accompanying deaggregation as well. Now, if I plug in those shaking hazard curves into a lateral spread model for a particular site, I can get out what are these purple lines there, and then produce the lateral spreading hazard uncertainty, lateral spreading hazard curves as a function of annual exceedance probability on the horizontal axis. And so we can see, for a given event, scales don't quite line up. So I've just shown for the red line a sort of 1 in 500 that we could end up with a certain range of lateral spreading being predicted. That might be in the order of 0.5 meter to 1 meter, and that supposedly is a fairly wide range. And structural engineers, if that's what geotech engineers gave, they're deciding that's a big range. What number is it? Well, let's actually step back and think about the realities. Lateral spreading is not just governed by PGA, but also by magnitude. And in module 1, we can pick out a mean magnitude, or a mean magnitude is given a table, and away we go, and we get an awfully precise number, somewhere between 0.5 meter and 1 meter of lateral spread. But looking back at the deaggregation, there's a whole lot of contributing hazard sources with all different magnitudes, from low magnitudes right through to larger magnitudes. So when we bring all of that information from the deaggregation right into the hazard model, all of a sudden we start finding that the range of uncertainty in a lateral spread prediction for a 1 in 500 year event goes anywhere from 10 millimeters through to 2 meters. We can get awfully precise in our numbers if we just pick a mean magnitude, or and just think that that's the number I've calculated, and become quite certain when actually we don't have those levels of certainty. So keeping all that uncertainty in mind, let's just sort of move now to an example, and I've just picked a sort of small, quiet suburb, in the Otago area, Glenorchy. It's able to use this one because it's a report that's publicly available and published. And we've got all the elements here of a bit of a problem that occurs, or a step change between SLS and ULS. So we've got a delta fan here that's built. It's been built up over time. It's been built up while the lake levels were higher and deposited underwater in a low energy environment. Subsequently, the lake levels have dropped in Lake Wakatipu, and you've got a sort of an overlay of delta deposits over the top. And so effectively there's 25 to 30 meters of loose to medium dense sediment, on this delta. About sort of 5 to 10 MPa of CPT tip resistance. There's a bit of a crust over the top, and there's a 25 meter high free face. So, when that liquefies, you can set up quite a potential for some lateral spread. And on top of that, sitting against sort of the eastern side of the township is basically a steep slope that goes up for several hundred meters. Got boulders and rocks and other things in there. So quite a lot of geologic hazard potential waiting there, in seismic shaking. And so if let's just sort of consider these points on the map here, areas D, C, B, and A, and we'll just look at some of the CPTs in the township. There's a sort of quite a number of CPTs undertaken in the township. I'll just pick 3 representative ones and taking them through a liquefaction triggering analysis. On the, you see sort of pairs of 3, that's sort of 3 CPTs. The green is where liquefaction is not predicted to trigger. The red is sort of where it's predicted to sort of well and truly trigger. And along the horizontal axis, we've got the shaking intensity, the PGA, and the corresponding return periods based on the module 1 values. And we can see at a certain point, at about sort of a, liquefaction triggering is expected. Now at SLS, nothing's going to occur, great. And at ULS, full liquefaction triggering is predicted, about 15 to 20 meters of material that's predicted to liquefy with about sort of a 4 to 5 meter thick crust. Now 4 to 5 meter thick crust would normally be sufficient, but with such a very thick deposition of liquefying material, it's not. And so at ULS, we could expect ejecta, differential settlement, deep liquefaction. Now, when we consider the free face, and I'm just sort of taking the median lateral spreading calculations, that effectively for different levels of shaking intensity or different return periods based on the module 1 values, we can see the lateral spreading starting to increase. The horizontal axis is distance back from the free face, and the vertical axis is the magnitude of lateral spread. And what we can see is as the shaking intensities, the return period of shaking intensities increase, not only is the lateral spreading increasing, but also the distance back. So the more soil profile or the more of the township that engages. So now if we think about Site D got a lateral spread issue and quite a severe lateral spread issue at ULS. And ideally, if you could avoid that site and had a client who sort of had a number of sites that they could choose, it's probably a good site to avoid. Site C is about 600 meters back from the free face. And it's outside of the lateral spread zone for ULS. So you might be able to come up with some type of foundation system to sort of deal with the ejecta differential settlements. And so Site B is well and truly outside that, and Site A, well, that is too. But the thing with Site A is there's some other geologic hazards to consider of the slope all above it. And so you might have a stable building platform, could engineer your foundations well, but just sort of end up with a landslide, piling up on top of it. Right. But if we think about Area C, and if we start thinking about the uncertainty both in our geotechnical calculations, the uncertainty in the shaking hazard, if the intensity was a little bit higher, we might well end up with Site C engaging with a little bit of lateral spread beyond ULS, slightly beyond ULS. So if we haven't allowed for that in our foundations, we could actually get much poorer performance or undesirable outcomes. So it's really important to start thinking, once we bring the uncertainty into consideration, of what does that actually then practically mean for the design considerations. So this is now where Andy will use that example.
It's a highly documented design of a industrial warehouse facility that's going on one of these sites. And so it's a fairly typical design. We have some precast perimeter walls. We've got some portal frames transversely, and we've got some cross bracing in the long direction. And just for this example, we have the cross bracing going down to ground. So the designer of this portal frame decided to use a fixed base to get a nice, efficient column and rafter design. And to do that, in this case, they've used a cast-in stub into a foundation beam element. And so if we put this design in a couple of those two locations, perhaps if we selected Site C, at least at the ultimate limit state, then we perhaps have a differential settlement issue, but we don't really have the problem that Sites A or B would have with the issues of being so close to that free face. And if we start to draw out and think about, drawing some diagrams which help to convey the performance, we see that the consequence in Site C of differential settlement is ejecta, differentially dispersing to the ground surface, getting some settlement of that pad. Possibly we'll also get some rotation of that pad as it settles. We may not necessarily get a loss of fixity. We don't necessarily have a punching or a bearing failure issue here. It's really just significant deformations or settlements in the ground and the high likelihood that those will happen differentially. So we probably, still retain more or less the same stiffness in this frame, but we definitely were going to be seeing quite a bit of strain and redistribution across that frame. So before we think about ground improvement or very heavy foundation interventions to try and deal with this issue, we can look at how the structure can tolerate that. And there's a few simple things that can be done, some of which may already be in place as a result of designing a structure like this in a relatively high seismic zone. So at the knee, we have an SENZ standard limited ductile moment end plate. We have a category 2 beam and column section. We have fly bracing to keep those sections fully laterally restrained. Seem to have omitted that on the column. We should have some there too. And in the long direction, we have full capacity bracing connections, already a requirement if we're using rod bracing. But even if we're using angle or flat bracing, we can choose to make those connections full capacity as well. We have a collector strut, and just simply by resolving capacities into angles, we can provide a collector strut that delivers the brace capacity. At the foot of the precast wall, we can take our traditional details and we can use the really good information in this Concrete New Zealand report TR78, which looks at the real performance of these precast panel base connections and their deformation compatibility out of plane, and look to provide a detail that can sustain significant out of plane displacements. And that allows us to turn around and say, well, we do have some potentially significant redistribution that might occur, but it's actually possible to quantify that and look at that against our standard sort of fixed base simplified structural model and say, well, from a ULS design perspective, there is actually a way through this problem which avoids the need for excessive or potentially costly ground improvement and so on, provided that the client's happy with the level of damage that's implied. Moving this building a bit closer to the free face, or starting to fold in some of those considerations around uncertainty and the likelihood that we could see some of that lateral spread and that stretching it back a bit further up the face of the valley. We see the obvious reason why always, notwithstanding how we think the ground might perform, that always we need to be tying foundations together. If we provide a foundation beam, then if we have some control over the size of the footprint of this building, maybe we look at the orientation of it. Perhaps we can do a simple number on what the capacity required of this tie beam might be. We can actually find a way to help force those strains to actually occur outside the building footprint and actually minimize the stretch that we see in this building, let alone the need for it to tolerate it. These are all things that are presented here in the context of trying to tolerate some of the things that are happening with the ground. But of course, they're things that we should really be thinking about doing anyway, geotechnical aspects aside, to deal with some of the uncertainties in shaking and structural response regardless. If we shift that site to Dunedin.
So same site, could be Kingston, but Dunedin, much lower seismic hazard zone, shaking intensities all comparatively drop. And so all the return periods shuffle up considerably, taking now the module 1 values for Dunedin. And all of a sudden we see, that even at 100-year, we don't have any lateral spreading. There's no liquefaction triggering. By the time we get to sort of ULS, there's a little bit of lateral spreading, but site C would be well and truly outside. And given it's only minor lenses of lateral spreading, of liquefaction triggering, at SLS, nothing's occurring. And at ULS, we get some liquefaction, but there's a fairly substantial crust there. We'd only get very minor differential settlement in areas A to D, and it's only really beyond ULS that we start getting ejector differential settlement and deep liquefaction, and D coming into a lateral spread zone. So theoretically, if we're applying code minimum, we wouldn't need to do any of this stuff, and just something like that is fine. Well, those things that Andy talked about, because there's no problem at SLS, there's no problem at ULS. If we consider the uncertainties, both geotechnically and also consider the uncertainties of the shaking hazard, if we had an intensity that was just a little bit more than the precise values we pull out, if we had the magnitudes or frequencies or some of the things that we simplify earthquakes down to a PGA value and a magnitude, but they're not all the same. There's a whole lot of other characteristics that describe earthquakes as well that we're sort of not even capturing in those simple parameters. That would result in a slightly different behavior, and we'd end up with needing a design that looks like that. Does it make good engineering sense to sort of be on this side of the line and design it this way, just slightly over that side and have a different design? Shouldn't we be sort of looking beyond and allowing for that uncertainty? So that's a really good example of in a lower seismic hazard zone beyond ULS that it would be good prudent practice as per the sort of what the guidelines are suggesting to sort of if there's step change that we need to sort of prudently allow for that. Now, for this example, we could also consider a different type of building, where the groundwater might be a bit shallow, and there could also be, issues, and Andy will just talk to that as well.
Yeah, so as Sean said, it makes little sense to see a substantially different design outcome when we're sort of one or either side of that line. Perhaps we might shift mode slightly as designers and realize that the intent here is not to apply a ULS design process at a level of shaking beyond ULS, but we do need to be thinking about really testing that design a bit more conceptually, considering its behavior for a collapse risk. And so maybe a slight change in approach to the way that we think about design, but seeing that the outcome isn't really all that different. This building in the Dunedin site, if we again saw those sorts of differential displacements, and if we'd applied the level of detailing shown earlier, then clearly we can see that there's no collapse risk and that we are fine to go on. An interesting little sidestep into what this looks like for something which isn't constructed from the materials that we're so used to, being concrete and steel. And this idea that we talk about ductility and we talk about capacity design and we talk about full capacity connections. But if we start to think about timber structures, and again, in this Dunedin example, we're really quite focused on what is the tolerance of the structure to some of these uncertain deformations. And there are ways in which we can detail connections in timber to make sure that they do behave in a ductile manner. And our new timber standard forthcoming, a little birdie told me it's very, very, very close to being published, will give us the tools to apply this sort of thinking to connections in timber. What you're seeing here on the page it's not a portal frame connection. This is an example of a CLT wall. But kind of the principle applies. We're seeing something which is a little bit different to our conventional idea of ductility. There's a lot of softening and there's a lot of slop, but we're seeing a connection that can retain its strength and not completely lose capacity. And certainly that passes the test of allowing us to say that we have collapse resistance and we have good tolerance to uncertainty. Taking that way of thinking and sort of bringing it into a much briefer and much more succinct example, and that idea of testing for collapse potential under liquefaction post-ULS. On the left, we have a simple example, probably still in a relatively low seismic zone, of a wall on a gravity footing on a relatively stiff crust. If we find that beyond ULS, we could have either differential settlement from ejecta, or we have a bearing capacity issue develop due to a thin crust, or both of those things. Then we can quickly see how large displacements in the orders of hundreds of millimeters could quite quickly lead to a very one-sided response and possibly reaching that point of gross instability, depending on the slenderness of this element. If on the right, we think about changing that footing system, maybe we can keep it shallow, but we can move to something which is able to engage the whole building stability. We use continuous columns, and maybe we even provide a continuous backup frame. Probably a bit easier in concrete than it is in steel, where that might be a bit more expensive. But largely it's just thinking about, can we test this design to that same sort of order of magnitude, hundreds of millimeters of displacements, but all the same a relatively qualitative test. And we see that it passes that test far more easily. I have a few other brief multi-story examples to highlight a few references, mostly references back to the SESOC interim design guidelines. Our steel standard, particularly following the 2007 amendment, has a really nice structure to the way that it categorizes structures and provides that robustness. But notwithstanding, there are quite a few clauses to flick between, and sometimes a bit of a loss in clarity as to whether we're actually ensuring that good behavior, particularly when our chosen design ductility is low. We can get a bit trapped in the step-by-step detailed design procedures, and it's good to zoom out a little bit. So this is an example of an outtake from the SESOC guidelines, the new ones, that helps designers to be assured of a good global behavior. Proper axial load protection, ductility in columns. Either that can be done by a full unlimited capacity design or a reduced version of that, which uses a sway index to review likelihood of a full frame sway. Pretty similar to that used in assessment, similar to that which already exists in our concrete standard, and clarity is given on axial load limits for columns and categories that go along with that. Hopefully helpful and practical guidance. Similarly, although ductile brace frames have obvious benefits and have their own recommendations, CBFs are a simple system that does see a bit of use. What we see most often is that they're designed elastically because designers rightly recognize that they don't perform all that well as a ductile system, and they choose a different system. But elastic CBFs are often also designed elastically and detailed elastically, and the minimum requirements for those are quite lenient. There's some recommendations given on how we can be a bit more confident of getting this rather than these two on the right. So the guidelines include some detail on that as well. And if we go beyond squatter wall buildings and move into sort of the more slender, taller cantilevered wall types, there's a few comments to make there too. Our concrete standards got very good ductile detailing provisions, but normally ductile walls now enjoy a complete lack of cross ties, far reduced consideration of out-of-plane stability, and might even be singly reinforced. This here is one of a number of discrete cantilevered wall elements in a lower seismic zone, supporting up to 10 stories of building. It could be detailed as a nominally ductile wall. In 1982, there were provisions for a non-seismic column type which allowed light and non-ductile detailing, and all that was required to permit that was a slightly lower factor, the strength reduction factor of 0.7. And experience has obviously shown us that that approach was flawed. It's also required expensive programs of reviews and retrofits, not to mention some of the tragic consequences. Although well-intended, there's a certain irony that singly reinforced in our walls in our concrete standard have now been assigned a lower strength reduction factor of 0.7. This wall here is not singly reinforced, but the idea of a completely unconfined wall, tall wall, is quite uncomfortable, and there's really good reasons that a developer would wisely agree that a few extra strips and prefabricated hoop cages should absolutely be provided. So limited ductile detailing has been provided in this wall hinge, nominal confinement to boundaries above that zone. The designer shows a slightly thicker wall thickness to help fit that confinement and add stability, and we're able to reduce the wall length a little bit as a result. They thought about wall elongation and geometric rotation when looking at the floor intersections and the collected details. And they've also been working closely in Common to help ensure good execution. A few comments on regularity before I move to a close and pass over to Mark. Regularity is one of the more difficult ones. Our standards have some definitions around regularity, but they're used for little more than telling us which analysis method to use, and a small penalty at times on the way that we scale our design actions. Other standards internationally have stricter limits and actually apply quite rigid limits on how far you can go with irregularities. And we need to sort of change our way of thinking around that too. Rather than use it specifically for the purpose of identifying which pathway we travel through 1170 and how we apply that analysis method, we really should be thinking about minimizing and avoiding them. There's a few references pasted here. We obviously have the provisions in our own design action standard. There's a broader set of classifications in ASCE 7. And there's a couple of documents that I've put in the middle which provide some helpful commentary, particularly this interesting one in the middle right, Designing for Earthquakes, a Manual for Architects, helping us to put some of these considerations into language which is a bit more relatable and help our friends and peers on design teams recognize that this is actually quite a reasonable strait that often has benefits which are in common with other parts of the brief, such as driving efficient, cost-effective designs. The final few slides, again, before I hand over, very brief prompt for clear and consistent communication with our clients. This is a repeat of that same message, which I've alluded to before, so I won't read it again. And a simple example, not necessarily SESOC vetted, but an example of a section that can be easily added into a design features report entitled something along the lines of earthquake hazard uncertainty and building regulation updates. Set out the process from here in simple terms for our clients, make a recommendation, agree with them what level of performance they're after, and record some decisions around how that's been applied to your design. Working with consistent language and a common means of communication as we talk to each other and as we talk to our customers will help us work through this period of the next few years with all the much more ease and really start to elevate the importance of some of these really key principles. Right, thanks. I think we're going to skip on questions and hold them to the end, and we'll let Mark run straight on in.
Right, kia ora koutou everyone. My name is Mark Willard. I'm a structural engineer and principal advisor at the Ministry of Education. My part of the three course act today is to talk about how we specify school building performance in our structural and geotech requirements document. As it has many synergies to what's been described today and the Designing for Uncertainty document that's been released by the technical societies. So just by show of hands, how many people here are familiar with our engineering SGR structural and geotech requirements documents? Good, so about half. So no, that's really good. It's a document that's been out for a few years now, and many engineers are familiar with it. And for those that haven't seen it or aren't familiar with it, it's another really good reference material or reference document to read, particularly as we start this conversation around what future building performance looks like and any change to building code in light of this updated seismic hazard model. But first, a little bit of background around why the Ministry has its own engineering guidelines for designers, and that's really around the large scale of our school portfolio. So there's nearly 2,100 state schools scattered across New Zealand with 15,000 school buildings. Those are your halls, your gyms, your admins blocks, and if you were to start considering your ancillary structures, that would easily double to over 30,000. So the number of sites and the number of buildings means we have a really large property portfolio, about $30 billion in replacement value, and we're spending upwards of about $1 billion a year, either upgrading existing school blocks or building new blocks or new schools. I think last year that was even upwards of $1.5 billion, so a significant amount of investment going into schools at the moment. In terms of the building portfolio itself, about a fifth of our buildings have been built in the last 20 years. A third of our buildings are more than 50 years old, so well past their design life. And we've got about 100,000 teaching spaces needed out to 2030. So that just represents a large number of new school buildings or new school sites that are needed over the next 8 or so years. And with those new buildings and new school sites, we're finding that there's an increased demand or desire for multi-storey school buildings, which predominantly historically have been 1 or 2 storey and of timber frame construction. This need for multi-storey buildings is really driven by the rapid population growth in some areas like Auckland, Hamilton, or in cases where we have quite limited land available, and that's often in CBDs and in other places. And so in this case, we recognise that our land is our biggest asset, and we need to preserve that for the future growth of that school. And so going up rather than outwards is the strategy that's favoured. Now, outside of the usual 9 till 3 teaching and learning, schools are also used for adult evening classes, weekend sports events, church events, and community get-togethers. So schools are social hubs, not just for the kids that attend, but also for the wider whānau and community. This often means that schools are an essential part of their community and do play an important role following an event such as an earthquake. This was clearly apparent after the Canterbury earthquakes in 2010, 2011, where schools were used as community centres, housing centres, and local distribution hubs for getting water, food, and other staples around to people who had lost their houses. So schools therefore have quite unique requirements, and those requirements were never meant to be considered by the minimum building code regulations. So recognising the specific nature of schools and the specific societal needs on them, we've gone ahead and developed our own requirements which extend those minimum building code requirements and make the requirements specific to our structures, and as part of achieving our wider objectives around sustainable portfolios. So the document that talks to the engineering design, specifically the structural and geotechnical design, is the structural and geotech requirements document. So this document was first released in 2015, and it represents an early example of adapting low damage design to ensure that post functional use of buildings in an earthquake. It's important to note that while I'm specifically talking about the engineering document, we also have other documents which have above code requirements, namely our fire design requirements and weather types. And this is all based on our experience of our portfolio over the last couple of decades, where we see, as an example, leaky buildings, just a real gross inadequate performance of historic building design, and we're not wanting to repeat those same mistakes. So some of the key messages in the document, they really focus on good design practice. So fundamentally good design practice, similar to what Andy and Shord were alluding to in the Designing for Uncertainty document. Primarily, it's about getting the engineers together, collaborating, and the lead designer, because they can have some significant influence over the chosen structural scheme and foundation system. So it's really important that we understand the geotechnical opportunities and constraints for a site. So Shord was talking about the building. Do you buy a site which is close to that free edge, or do you purchase a site a little bit further? Now, historically, the ministries tended to purchase the worst sites, but hopefully that's changing with some of the thinking that we're bringing through now. But even on a site, you can get quite different performance depending on where you locate the building. So locating a building in one location can result in much better building performance and often cheaper foundation and structural systems by doing so. And because we want to put the money into the teaching and learning, not necessarily the foundations, we really encourage the geotech engineer and the structural engineer to get together and inform us about what are the best options. Shord also talked about understanding the level of earthquake shaking that initiates liquefaction. And that's really important to us as well. We'll talk about some of our performance requirements and the introduction of an SLS2 level shortly. But it's no point having a building that is designed for SLS1, no damage, ULS collapse prevention, only for that building to be severely damaged and a level of shaking that's slightly higher than your 1 in 25 year term period. We've got a really good example that I'll end with, which kind of talks to that. But the key message is really simple, regular structures, remove unnecessary complexity. It's a message more to the lead designers rather than the engineers, but you guys can certainly influence that. Limit building movement for improved building performance, and ensure you have a good hierarchy of failure. So detail for ductility, regardless of whether you're using that in your selected system. It's important to note that this does not add significant cost to your designs. So we did a recent example in Wellington where designers were asked to go and look at minimum building code requirements versus in this case, a site-specific hazard analysis on top of our SGR requirements. And for a $9 million build, the higher requirements plus the site-specific hazard analysis in Wellington came up with a $200K difference in terms of build cost, which I'm sure many of you would consider is not a significant difference when you're looking at a much more resilient structure. So a lot of the messages that have been presented in the SGR is very much aligned to the messages that are given to you in the Earthquake Design for Uncertainty document. So in addition to the previous good design practices, we also specify specific performance requirements for school buildings, and we introduce an SLS2 or an intermediate level of performance to really delay the onset of damage in our structures to much larger levels of shaking. So at that intermediate level, we require that schools remain usable, and that doesn't mean that there's no damage. It just means that where there is damage, that doesn't impact the safety, access, or egress to that building. And where there is damage, that damage is limited and can be repaired within a reasonably short time frame, which for schools, we've defined as a 2 to 8 week period, which reflects the school holiday shutdown period. And because schools are required to remain usable, it extends not just to the primary structure, but also to the non-structural elements, your cladding, your ceilings, partition walls, and also some of your building services. The intermediate level of performance is defined at SLS2 return periods. Now, these have been set similar to what you would have for civil defence buildings or other importance level 4 buildings, except scaled down for school purposes. Again, linking back to what Shaw was mentioning in his presentation, it's important that even though we've defined our SLS2 for at 100-year or 250-year return periods, we really want the geotechnical engineers to tell us if you're getting liquefaction initiated at much lower levels of shaking, and feed that information to the structural engineers so that we can get better performing buildings at the more regularly occurring levels of earthquake shaking. So what are the performance criteria? There's the usual SLS1 and ULS. SLS1 is very similar to the building code, where at low levels of earthquake shaking, the school should be able to be used as normal with no loss in amenity. This means there's no loss in the ability of the structure to resist future earthquakes. The non-structural and secondary elements remain intact. Building services remain operational. Readily repairable damage is permitted, provided that can be repaired immediately or as part of a usual building maintenance schedule. The SLS2 performance criteria does go beyond building code requirements, and this captures more significant levels of earthquake shaking. And fundamentally, this represents what we experienced in Christchurch after the Canterbury events, where we had the September event, followed by the Canterbury event. And so we've got a requirement there that a school building should be able to withstand an SLS2 event, and then immediately after be able to sustain a ULS event with acceptable performance. Some reduced amenity is accepted, provided that the building can continue to be used for its intended purpose and that the building can be returned back to a normal state within that 2 to 8 week time frame. At major levels of earthquake shaking or a ULS event, it's fundamentally the same as building code, with the 2 exceptions that we require our connections to site infrastructure to be designed in a way that they're repairable, and that the foundations are designed to ensure that they're not the weakest link in the hierarchy of damage. There's no point designing a really robust, resilient superstructure when your foundation is going to perform really poorly and ultimately require that building to be demolished. We saw too much of that following the Canterbury earthquakes, and so there's a requirement that the foundation is not the weakest link in that hierarchy of damage. So in addition to these broad descriptions of performance requirements, we also provide detailed guidance for how designers can achieve them. So in this case, for the primary lateral resisting system, again, we provided some qualitative statements around the SLS1, SLS2, and ULS performance, the key one being the middle one there, at SLS2, where the structure should maintain capacity to resist additional displacement from a full ULS event. The guidance also extends to non-structural elements with, again, a description of level of damage that we're expecting for the different levels of earthquake shaking. In this case, ceilings should not be damaged at SLS1. They should be repairable at SLS2, and at ULS, they can be really badly damaged, but must remain intact to the structure so that they don't represent a falling hazard to people within the building. So in addition to the qualitative statements, we're also providing quantitative guidance around limiting building movement at that SLS2 level. This is the lesser of the values in the table there, all that determined by deformation compatibility, which often ends up leading or driving the design, particularly when you have firewalls or smoke separation walls. So fundamentally, we turn the whole design process around. Rather than focusing on ULS loads and then checking for SLS1 drifts, we design the structure based on our SLS2 actions and limiting those drifts at the SLS2 level of shaking. And then we check compliance for ULS and SLS1 drifts. We also have some other design requirements, and that's all around providing regular building shapes. And for areas that are susceptible to liquefaction or settlement or are in settlement prone ground, we have recommendations for subdividing that building into smaller chunks with an aspect ratio of 1:4 in terms of length and width. And that really aids sort of the repairability of those buildings and means that you don't get concentration of loads affecting the entire structure. It's important to note that also it helps with, well, regular buildings help with weather tightness issues, where we have run into quite a few issues historically. As well as detailing the lateral system for ductility, we also have a requirement around all significant load-bearing elements. So those are your gravity columns or even your gravity wall elements to be detailed using the geometric requirements and the relevant material standards for ductility. And we have a priority or trying to promote the use of lightweight materials for the structure, as this reduces both your seismic demands on the structure and promotes the use of shallow foundations and potentially gets away with some of the deep pile solutions that we see. So as part of our coming to a design for a school, we also asked the engineers and the design team as a whole to look at various options. And this is really to help inform our asset management colleagues around whether it's worthwhile investing more money to having a more resilient structure or not. And so this is just an example of a table which looks at one option. What is the initial capital cost for that option? And then what is the expected repair costs at the different levels of earthquake shaking? So again, you'll probably have two of these tables comparing two different options, but that is just a really good, clear way of communicating building performance to people who don't speak engineering language. Now back to the case study I alluded to earlier. We've got a really good one of a school that was built in 2010. This was prior to the introduction of this document, and the building itself met building code at the time, and that no damage is expected in a minor level earthquake, so 1 in 25 year event, and there's no collapse at the 1 in 1,000 year event. Fast forward 10 years from when that building was designed, there's now stage 2 that's required at that school site, and stage 2 looks like connecting onto the original stage 1 buildings. Because of that interconnection between the new and the old, we asked the engineers to go away and have a look at how that original stage 1 structure performs under that SLS2 level shaking. So the engineers went away, and this site in particularly has a liquefaction problem, and that liquefaction is initiated at a 1 in 100 year event level of shaking. So ultimately that means that that stage 1 building has a 50% chance that it will be damaged beyond repair in the next 50 years. Now, if that stage 1 building was built to the current ministry's requirements, It would still meet building code requirements, but then it will also have a repairability criteria, and the engineers would have paid a bit more attention around some of those lower levels of earthquake shaking between SLS1 and ULS. And that wouldn't have looked like much more. The stage 2 buildings just have a slightly more robust foundation and greater ductile detailing in the superstructure. So while that comes with a slight cost premium at the onset of the design and construction, it has significant cost savings for our portfolio over the life of that building. So for those that aren't familiar with it, if you want to read the document, just Google MOE SGR and you'll get taken to a link with the document, which is freely available to download. There's also a 2-page summary sheet there, which you can give to your architectural colleagues, which describes the principles quite succinctly. And we've got some other useful templates on our webpage as well. Now, a lot of people talk about, well, how do you get the architects to kind of buy into this whole resilient design or adding additional robustness to your design? And I think the answer to that is around what we're seeing also out there around the changes around calculating your whole of life embodied carbon and the drive in the industry to lowering both our embodied carbon, but also our operational carbon aspects. So resilient structures and structures that are capable of resisting a wider range of earthquake shaking fundamentally have lower embodied carbon calculations over their whole of life when you do the assessment. So not only are you ticking the resilience box, but as we start to see more and more of the targets put in for embodied carbon, you're going to get architects wanting to drive this whole approach around lower embodied carbon. And that's not just through substituting concrete and steel for timber. There's more deeper fundamental issues around resilience, which help achieve those objectives as well. So I encourage you to talk to your architectural friends, and I'm sure they'll buy into the whole resilience piece when you pair it with the lower life cycle carbon costing. So that's all I've got today. Yeah, happy to have any questions from my presentation or Andy and Sean's.